Hello, I'm Seulgi Park. I'm a PhD student from Seoul National University, Korea. This work was performed as part of an internship at Naver AI Lab. Now I'll present our work, The Majority Can Help the Minority, Context-Rich Minority Oversampling for Long-Tailed Classification. In practice, many data often exhibit long-tail distribution. The model trained on such imbalanced data tends to overfit the majority classes. Therefore, long-tail classification aims to make a robust model while training on the imbalanced dataset. One important direction to overcome the class imbalance problem is to oversample the minority classes. One of the commonly used methods are random oversampling and synthetic minority oversampling technique called SMOTE. Random oversampling repeatedly oversample minor classes, and SMOTE generates new minority samples by interpolating between existing minority samples and their nearest minority neighbors. However, when the imbalance ratio is severe, these methods can intensify overfitting problem because the oversampled minority classes have less diversity but almost similar image contexts. Recently, more sophisticated oversampling methods have been proposed. GAMO produces new minority samples by training a convex generator, and MetaSEG uses implicit semantic data augmentation algorithm to generate diverse minority samples. However, they require high training costs such as training a generator and requiring additional balance validation data and hundreds of iterations for training. Therefore, we need a simple and context-rich oversampling method. To generate diverse context-rich minority samples from long-tail distribution, we pay attention to the characteristics of long-tail distributions. That is, we observe that majority class samples are data-rich and information-rich. For example, consider a minority class of snow goose in which the geese always stand up in grass in the training images. Repeated oversampling or interpolating within the class can only create similar images as in the figure. However, our key idea is to use the rich major class images as the background for the newly created minor class images. Then, as shown in the concept figure, we can create images with more diverse contexts. To combine two different images, we adopt CutMix data augmentation. Since CutMix is originally designed for class balanced dataset, naively using CutMix generates more samples of the majority classes. Therefore, for an imbalanced dataset, we propose to use different distributions for background and foreground images. Here, background image XB follows the original distribution to sample diverse contexts, while foreground pitch XF follows a new minor class weighted distribution so that we can oversample minority classes. As shown in the table, CMO outperforms CutMix on long-tail classification by a large margin. Especially, there is a remarkable performance improvement in the medium and few-shot classes. This highlights the importance of using different distributions on imbalanced dataset. For the minor class weighted distribution, we designed different sampling strategies. For details, please refer to our paper. Finally, we present the pseudocode of the training procedure in algorithm. We validate CMO on the benchmark datasets with various imbalance ratios. As you can see, our method consistently improves existing methods and outperforms recent methods on ImageNet LT data. It is noteworthy that when trained for longer training epochs as in PACO, our simple augmentation method outperforms PACO, which uses contrastive learning. To justify the proposed method, we conducted various analyses. For more experiments and details, please refer to our paper. In conclusion, let me sum up our main points. Thank you for watching the video.